Ladies and gentlemen, welcome back for our final session. It's a great pleasure to introduce Professor Subir Sarkar, who's going to give us a summary of the day's proceedings. The professor did his undergraduate training in India and a PhD in the famous Tata Institute on experimental and theoretical cosmic rays. He is currently working on particle theory in the early universe. Thank you very much.
Thank you. Good. You've had a very rich feast all day, and I can see you're still hungry, otherwise you'd have come back after tea. And I have the rather difficult task of trying to summarize a rather interesting and varied program, and which was about 2/3 philosophy and I would say 1/3 physics. And the philosophers, at least one or two of them are good colleagues of mine, but I should say at the very outset that my attitude towards the philosophy discussions such as we heard are not dissimilar to that of Einstein himself, our hero. He was once asked, and this is recounted by his secretary Helen Dukas, whether he wanted to go to a seminar that was being held at Princeton on the philosophy of relativity. And he said, no, I don't think I will, I'm busy. And Helen says, but Professor Herr Einstein, it's on your theory, it's the philosophy of your theory, you must go. And he says, when I go to these talks, I feel I'm swallowing something I don't have in my mouth. So, with respect, I did not quite feel the very same way, but nonetheless, I think that although it's perfectly legitimate, as our colleagues did, to question received notions that we have about things that we take for granted, about causality, about synchronicity, about the nature of time, about its flow, and all kinds of things which are built into physics right from the classical level onwards, and which acquire more and more mysterious aspects as you venture into the quantum world, and especially when you try to bridge the current gap between the flat space formulation of quantum mechanics and gravity, which has not yet been done entirely, although we heard about some interesting developments along those lines in Alan Heavens' talk. So these questions are perfectly legitimate and they should be asked. But let us remember that at the end of the day, as Harvey himself acknowledged, and as Alan gave us some numbers about, all of us are carrying around today technology in our pockets which actually relies on its success, on the correctness of all these theories with their vexed notions of time and space and what have you. In particular, your GPS works to within 30 meters because you make a correction for the fact that the Earth's orbiting, you're moving at a certain velocity on its surface, so you have a time dilation due to a special relativistic effect, but at the same time, because you're in a gravitational field, clocks run slower, and that gives you a general relativistic effect. And we saw that these values have to be calculated according to the known laws of physics that we have in order to give us a workable system. And the bottom line is it works. We all know it works, right? So let us by all means indulge ourselves into thinking about these notions, because only by examining them in as rigorous a way as we can, and by challenging received wisdom, which is often, as they quite correctly pointed out, very circular in the argument. Nonetheless, if you are an empiricist, if you are in particular a physicist, a natural philosopher, if you will, as I am, my proof of the pudding is in the eating. Does it work? Can I calculate it? Can I measure it? Can I test it? Yes. In that case, I'll be happy for the moment, and I'll leave worrying about the fundamental nature of it until I retire, okay? Because that's exactly what Kurt Gödel did when he was asked what he was working on after he went to the institute in Princeton, after having done his famous incompleteness theorems and having invented a spinning universe and all the rest of it. He is asked, what do you work on these days, Professor Gödel? We are asked such questions by our research councils when we ask for funding, and you have to write pages and pages of rubbish. Gödel could just say, I'm thinking about the nature of time. And I wish we could say things like that today, because that, of course, is a sufficiently big question and one that has occupied us all day today. However, let me add that Gödel never actually made any substantial breakthrough in our understanding, perhaps for himself. We can all clarify our own thinking in this matter. But ultimately, what really makes an impact is, do you find something that you can write down in mathematical form which is subject to experimental test? That is the way physicists see the world. Okay? Or to put it much more bluntly, shut up and calculate. That's what we say. Okay? We don't indulge in philosophical torture of notions that seem to work as far as they are amenable to experimental test. So let me start with just one or two. I'm not going to, by the way, I should make it quite clear, I have absolutely no intention of trying to review people's talks or of providing a summary. The talks were perfect in themselves. They spelt out their territory in no uncertain terms. They were engaging, they were provocative, and I certainly will not try and, there's nothing to summarize in that respect. What I would like to do, however, is to dispel one or two misunderstandings that appeared to me to be quite pervasive, and one of them concerns the arrow of time, and the other one is much sort of more general, which is what I'll start with now. We were told, or rather we heard, various things about causality, about, of course, it seems it is dangerous to say something, as they would say, bleeding obvious, like, cause comes before effect, because then you would say, well, does it really? What do you mean by cause, and what do you mean by effect, and what do you mean by before? Yes, indeed, but we all know that cause comes before effect, so that's that, right? And if you want to put that down mathematically, then you say that, as Minkowski famously did, Einstein's teacher, if you will, that you can divide the world into what we have experienced and what we are yet to experience, and the present is truly unknowable. The present for me does not exist. The present is where you are, and I'm not going to know about you until a few nanoseconds later, right? So I cannot actually know exactly what is happening in the present ever. That is because that is just that point there, right? We only can observe along our past light cone. Some observations, of course, we can make along our past world line. If something that is just sitting on the table, not going anywhere, that I can do. But regardless, everything is always within my past light cone. And this is actually taken from a lecture I give on cosmology to illustrate that we do these measurements only at one particular point in the universe. We do not move around the universe and make measurements from everywhere. We have no way of comparing the past light cones of somebody on this planet with somebody in Andromeda, far less somebody on the Hubble radius away. So we really don't know what the universe is like. We can never know what the universe is like, apart from what is on our past light cone. That's all of astronomy is there, because light, of course, travels at the speed of light. That's all on the red cone. Now, this leads to a philosophical problem, that when we talk about special relativity, of course, that was constructed in what we now call flat space-time. But let us remember that before that, there was just space and time, and Einstein's great insight following the observation that Maxwell's equations allowed propagation of something at a speed that was given by some permittivity of empty space as it appeared. Those disturbances, he realized, had to be invariant for all observers, and that is how we got to the special theory of relativity. But that is all constructed in flat space-time. And we are doomed to be sitting here in this planet, in this room, which is basically special relativity. We do not see the effects of space-time curvature here. As Alan mentioned, a gravitational wave did pass by. They're passing by all the time. But they actually curve space very, very little, extremely little, for all practical purposes. And this is the acronym which we often use in theoretical physics, FAPP. For all practical purposes, space-time is flat. And we are restricted to making observations along our past light cone. We cannot actually know what is happening over here or happening over there, and therefore, to some extent, we have to invoke philosophical principles only in cosmology and nowhere else in order to construct a physical model. In this particular case, it is something called the Milne cosmological principle. Milne was actually the Rouseball professor of mathematics here. That you need to do because otherwise you could not ever construct a model of the whole universe from your own particular vantage point. But this already tells us a lot of things. We have drawn here a vertical line that is supposed to be the time coordinate, and this whole discussion today about what is that, can we actually define it independently of the measurements that we are apparently doing to determine it, and the circularity in such reasoning and all the rest of it. But the bottom line is that all those measurements that we make within the past light cone work very well indeed. They substantiate the assumptions you made, everything fits together, there is no problem. There is no problem, I emphasize again, right? Now let us go to this issue that came up with regard to the Big Bang and can time exist before it and all the rest of it. So I recall Hawking's famous answer when asked is the time before the Big Bang was to ask, it's the same thing as asking what is north of the North Pole. By definition, there is no time before the Big Bang because that's how it's defined. So let me remind you in 2 slides how we actually define the Big Bang. What we do is we observe. We observe galaxies around us and we observe that they're all moving away from us at some speed, okay? And galaxies which are equidistant from us are all moving away at the same speed. If you look at galaxies twice as far away, they're moving away at twice the speed as indicated by the size of those arrows. So it is quite clear that if you reverse those arrows, then the ones which are further away will be coming in faster, the ones which are here will be moving in less fast. So they will all reach us at the same time. Okay. Now, of course, our position is not special. Remember Milne's principle that I just propounded. You could say this for any point, right? And therefore, we are led inexorably to this description that something of order 15 billion years ago, 14 billion years ago, which is the inverse of the rate of expansion today, something happened. Okay, and that something is what we call the Big Bang. It's just a word, it's a term. In fact, it was an insulting term invented by Sir Fred Hoyle, who didn't like the notion at all, but it has stuck. This is just a matter of definition to describe what we see around us in terms of an event, which necessarily is singular, the way we have constructed it, but in fact, we know nothing about it. We know nothing actually about the Big Bang, and we don't need to, because we are living long after it. Everything that we measure in the universe goes back to a certain point close to the Big Bang, but not quite at it. We only have gone back to, I think, 10 to the minus 10th of a second close to the Big Bang, which might seem to you to be very close. But remember, in the logarithmic scale, there is another 36 orders of magnitude to go before you actually get there. And the point is that as far as we are concerned, the space-time that we inhabit, the one that we deal with in our theories, in special theory, and then we augment it with Newton's constant to become the general theory of relativity, which then tells us how the energy momentum of matter affects space-time curvature. This is just a construct. This is the construct that we use, just as space-time is a construct that we use to make sense of events, in particular to give cogent meaning to the notion of causality that we have built into us. Okay? And this you can imagine as just being the antipodal point of some sphere. So imagine a sphere, this is the North Pole, we are sitting there. Light is restricted to coming towards us along the surface of this expanding balloon, if you will, right? It cannot travel outside this surface. Therefore, when I look out from my vantage point, I see the universe getting bigger and bigger and bigger and bigger, and then after I cross the equator, it's getting smaller and smaller and smaller. Ultimately, all the light from the Big Bang is coming to me along every direction on this sphere. Therefore, it fills the sky. The Big Bang is everywhere. It is not at any particular point in space, because this point I chose at random. Remember always that I have a symmetry on a sphere. The North Pole appears to be singular, as I think you mentioned in passing, that it's a coordinate singularity. It has no significance whatsoever. And we should not be distracted by artifacts in the mathematical construction, because we created it, we wrote it down, we know its limits, we know not to take it literally in certain contexts, but it means nothing. We're just wasting our time if you then worry about what's north of the North Pole. It is it's just a ridiculous question. Okay? And therefore, This, if you like, is the initial singularity in the sense that we are now trying to sort of propagate this in time. So let us say that we are thinking in terms of something being blown up from an initial singular point at which all of space-time and matter was created by our modeling. This is all a construct. Everything that we do in physics is a construct. Do not ask me, is it physically real? Of course it is physically real. Otherwise, why should I go to the trouble of constructing it, right? But, and I'm not trying to be facetious here, there is just total circularity in asking that question once I've gone through the exercise, right? I've created a model of what I see around me. The model is good if it enables me to predict things which can be measured and checked against the model, then it's good. And then the model keeps getting refined and refined and refined, right? Now at a certain point, the language starts failing. Our best physical theory in the universe today is called the standard model. It's actually not a model, it's a theory. It has been tested beyond the classical level, it has been tested at the quantum level. It has successfully passed every test, and yet we call it the standard model with the sort of false modesty that physicists sometimes have, believe it or not. And in this context, you might ask, what's the difference between a model and a theory? And I think the answer that I have heard that best encapsulates the distinction is actually due to Manfred Eigen, who I believe won the Nobel Prize for Chemistry. He said, a theory has only two alternatives. It must be right or it must be wrong. A model has a third alternative. It may be right, but irrelevant. Okay? We are interested in what is relevant. We are not interested in constructing possible worlds which are not relevant to the reality that we inhabit. And to the extent that we can only ever approximate the reality by a model, all our models will by construction be incomplete. There will always be effective theories. In fact, that is now the currently fashionable term for the standard model. It's an effective theory. The standard model works perfectly fine in the laboratory. It has been tested at machines like the Large Hadron Collider. It passes every test. But it clearly is not the final thing in the universe because it doesn't explain anything about the universe as a whole. In particular, it does not explain why there is matter but no antimatter. It doesn't explain why most of the stuff in the universe seems to be material which is not in the standard model, dark matter, dark energy, and so on. It doesn't explain why there are galaxies, why there are fluctuations. So we know there is new physics. This we always know. Nobody is ever arrogant enough to think that whatever theory that they have, successful as it is the end of the story. If it were, you would go off and do something else. Okay, we cannot continue to be physicists. So let's get back to some basics. What we do is we make measurements, we make observations, and always along a past light cone when you're doing astronomy. So you know that looking far away is looking back in time, and what we are doing in cosmology is just doing that. We are looking further and further back. When you look at the Hubble deep field, this is the deepest that we have seen with the telescope. We are looking back nearly to the beginning of the universe. It's 12 billion years. If you could go just a few more billion years, then we would actually be able to see the initial singularity. But we can't because the universe becomes opaque. It becomes so hot that the matter gets ionized. It's just like trying to look through a plasma, through the ionized gas in a tube light. You can't do that. But we have just discovered gravitational waves, and they are waves in the fabric of space-time itself. So to the extent that our model works up to a certain point, it definitely works up to temperatures of the order of 100 GeV back in the early universe. It may well work up to much higher temperatures, almost back to the initial singularity. And we will detect those waves one day, and then we'll know more about what lies beyond the sphere from which we can only see photons at the moment. We'll learn to see in other messengers. We'll learn to see in neutrinos. I work on an experiment that has just detected cosmic neutrinos at the South Pole. One day we might see relic neutrinos from the Big Bang. Not that experiment, but others. So let me now turn to another issue which I noticed created a lot of confusion, which is the distinction between the microscopic arrow of time and the macroscopic arrow of time. There are two arrows of time. Now, one is very familiar to us. If well, I'm not allowed to do it. If I light a cigarette or light a little piece of paper, you know what will happen. Smoke will rise from it, and then it will disperse in the room, right? And after a few convection times, the smoke would have dispersed uniformly through the room. Now, if you look at it in the microscope, what's happening? There are particles coming out. Smoke is just some molecule or the other, and it is scattering, it is doing Brownian motion, it is doing a random walk, it is going off from where it started. You know all about it. Einstein was, in fact, the first person to study that process, Brownian motion, in mathematical detail. Now, every step that every molecule makes is time reversible. If you run that film back, just a chunk of it will look exactly the same. But if you run the whole film back, it will not look the same. You never see a situation in which all the smoke in the room miraculously gathers itself and finds its way back into my little cigarette. Why not? It is perfectly allowed by the laws of physics. The laws of physics in this instance, which are just, elastic scattering, Brownian motion, is perfectly time symmetric. It's simply because of, you can give it many names, but a simple word is phase space. The number of possibilities for those smoke particles to disperse themselves in the room is much, 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 much bigger than the single possible way in which they can reverse their velocities and find all their way back to this point. There is nothing magical or mysterious about it. It's just a statement about counting. How many ways can I do that as opposed to doing this? And that is all that there is to the thermodynamic arrow of time. It's just a matter of what is your final phase space. Is it big or is it small? Okay? But that is not enough. We need also a microscopic arrow of time. And the microscopic arrow of time says that although all natural laws that we know do not seem to have anything to do with time, they are perfectly okay whether you go forward or backward in time. About in 67, so going back some years, two people, Val Fetch and Jim Cronin, and a couple of other people with them, they did an experiment that established that in weak interactions, okay, you know there are various kinds of interactions. There's gravity, there's electromagnetism, which is what the classical forces you're familiar with, but then there are also the strong interactions that hold together the quarks and the matter that we are made of, and then there's the weak interactions responsible for example, decay, radioactive decay. Those interactions do not respect these symmetries. Weak interactions violate parity, which is a major, major upset for everybody when it was first discovered. But moreover, they also can violate something called charge parity. When you reverse the charges of the particles and you reverse their parity, then you might expect to see the same process again in the mirror, which was violated by the parity operation alone. But they discovered that in the decays of certain particles called kaons, very, very rarely, once in 100 million times, you will see a process happening one way which cannot be time reversed. Okay? And this is very, very important, because if that was not so, then we would not exist. We would not be here talking about what we are talking about. And this is very, very important to understand. And this very recently has been established to a greater degree in the decay not of K mesons, but another kind of mesons called B mesons, doesn't matter what they're called. And graphically, what that says is that there is a distinction between two B mesons which are shown here, represented as colors. The blue ones change into the red more quickly than the red changes into the blue. Okay? And this is the process running in reverse time. You'll notice that the numbers on this dial are actually shown backwards. Right? This is a experimental evidence that there is asymmetry in time in a microphysical process that you can measure in the laboratory, in this case in an experiment called Babar, which is in Stanford. And well, you can't see it very well, but I'm just trying to illustrate to you that we have evidence of this. This is not something that I have to argue about on philosophical terms, try to convince you by the force of my logic and the persuasiveness of my hand waving. I can actually show you an event where this is the case. Okay? And well, you can't see it, but basically this is showing a decay process in which CP is clearly violated. But I think what you can see is that when the data are plotted quantitatively, you see a curve here. Okay? This is the evidence that CP is violated. If CP were not violated, the data would lie on a horizontal line. And I think from the back you can see that the data are certainly not consistent with lying on a horizontal line. Okay? We know that CP is violated. Now, very briefly, what does that mean? There was slight discussion about this in passing. There are various discrete symmetries. So this is going to take a more than one day to discuss, because this has taken about 45 years to understand what symmetries are and how they govern fundamental particles. That is most of our bread and butter business. But time, parity, and charge reversal are these three operations that are defined here. And what we know is that in any local relativistic quantum field theory, the product of charge, parity, and time conjugation is invariant. Okay? It has to be conserved. Otherwise, we will not have locality, we will not have causality, we will not have special relativity being correct and all the rest of it. Therefore, if CP is violated, then so is time asymmetry. Okay? So we do not actually directly measure time asymmetry violation, we infer it from this CPT business. And what that means is that we can exist, and for that I have to show you, just to illustrate that these are all mathematical statements, this is not just arguing for the sake of it. If that were not so, then if you look at how many particles should be left over from the Big Bang, which are, say, particles like us, we can study the evolution of the equation that tells us how much they change in time as the universe expands at some Hubble expansion rate, which is balanced by the rate of annihilations and the rate of creations, and the particle abundance will normally follow an equilibrium curve, but it will peel off from it when the rate of particle annihilations or creations falls behind the rate at which the universe is expanding, because if you like, the mean free path between particles becomes longer than the size of the universe. So never mind the calculation, the point is to just show you that we can do this calculation, and when we do that, we find that nucleons, the particles we are made of, are strongly interacting. They are the strongest interacting particles we know. They annihilate with each other with a cross-section which is called a barn. That's that big. It's 10 to the minus 24 centimeters square, but it's called a barn. And that would then give you a relic abundance of nucleons and antinucleons today, which would be 1 for every 10 to the 19 photons in the universe. So in every centimeter cube that you have in your hand, there are 410 photons from the Big Bang. So you can work out that 10 to the 1 in 10 to the 19 means you should get less than 1 baryon-antibaryon pair in whatever it is, a kilometer cube. However, what we actually observe is a billion times larger, and we don't observe any antibaryons. Somehow one baryon was left over for every billion baryon-antibaryon pairs. If that were not the case, then the universe would be entirely empty with all the matter and antimatter annihilated with itself, just a cooling sort of ashes of the matter that was there in the Big Bang. It would just be photons and neutrinos and nothing else, certainly not us, no structure, nothing. So it is crucial that we have to have these nucleons in order for us to survive. And that requires CP violation, because otherwise, as I just said, everything would have annihilated and we would not be here to discuss it. So graphically, I was trying to find there was a nice cartoon in the New Yorker which showed a chap counting sort of baryons and antibaryons, and it's got a huge pile on one side of baryon-antibaryon pairs and just the one baryon on the right-hand side. That's us, okay? We don't really, in detail, still understand how this happened. We know that in order for this to happen, as Andrei Sakharov told us long before we discovered this physics, you have to, of course, violate baryon number, that's why we are here, but you have to violate CP. Without that, you will not have the generation of this matter-antimatter asymmetry. Incidentally, you also have to have a departure from thermal equilibrium, because in thermal equilibrium, there is no arrow of time. Okay, equilibrium by definition means time doesn't matter. There has to be a departure. There has to be an arrow of time, even macroscopically. So you need both, okay? And both clearly exist in the universe. And in this process, we can clearly delineate the distinction between the two and their relative roles in determining the evolution, if you like, of the universe. So this is just to kind of highlight the fact that many of these discussions, rather than get caught up in words and go around in circles and worry about what is it that one is talking about, it is, I think, helpful to look at a worked example of what we know is the case. Even when we are grossly ignorant, we actually do not know how this really happened. The CP violation you measured in the B decay is far from sufficient to explain our existence. But conceptually, it is the same kind of thing. Okay?
Professor?
Yes?
Can I just clarify something?
Yes.
I think there might be I feel there's a bit of a misconception here because the conference talk was called The Nature of Time.
Yes.
It wasn't called The Nature of Time according only to particle physicists.
Indeed.
And so I think it's been a bit unfair on some of the people talking earlier because they're interested in foundational aspects, which are speculative.
Of course, yes.
But I think it's really important.
And indeed, we should talk about those, but ultimately we should talk about what we can, in fact, talk about sensibly, in other words, subject to experiment. Thank you for your comment. Yeah. So, coming to, I don't have very much more to say. So, currently the way we construct these world models, time begins at the beginning. We put a question mark there because, as I said, this is purely notional. We do not actually have a Big Bang. We never had a Big Bang. We construct a model to explain the world as we see it today. If extrapolated back along this coordinate, you would have initial singularity. Hawking and Penrose famously showed that with the energy content in the microwave background, it would be adequate to make that singularity inevitable in the absence of any new effects such as might arise due to quantum gravity. If you could also consider a universe in which is cyclic or bouncing, in fact, Einstein, when he was here in the 1930s and gave the Rhodes lectures, actually talked about the bouncing as a universe that expanded and then collapsed. It didn't come back to the singularity, but in principle, you could always construct universes which do that. Okay, here you are God. You just construct what you like. Whether it makes physical sense or not is the next step. For that you have to make measurements and test it against your expectations in a particular model. But what this makes clear is that we're just putting the time thing in by hand. We have no direct way of getting a handle on it because it is part of our construct. And once we have made it part of our construct, it doesn't really then make sense to ask, what does it mean? I put it there. I constructed the coordinate system in which I am at the North Pole. Then it makes no sense to then ask what is north of the North Pole. So, latest developments in fundamental theories, such as in quantum gravity, in particular in string theory, suggest, or actually we have moved beyond string theory, it's now called M theory or matrix theory. It is becoming increasingly clear that space and time are actually not fundamental concepts, but just as, say, turbulence in a fluid is an emergent behavior. It is not something that you can read off from the Navier-Stokes equations. Every motion of every fluid particle is governed by a law. It is reproducible, it is predictable, but then there is some new phenomenon that arises which cannot be a priori predicted from the dynamical laws, right? And it is currently suspected by our colleagues who work at this coalface, if you will, that it is in fact an emergent idea. And in particular, we can actually construct theories. This is something called the ADS CFT correspondence. CFT is a conformal field theory, which I don't have time to explain here. Anti-de Sitter space is a space which is negatively curved out to infinity and has a boundary at infinity. This equivalence, whatever it is, which I do not wish to explain now, shows explicitly that you can in fact have a theory where all the degrees of freedom in the theory, degrees of freedom is something you're used to. The properties of the particles that are flying around here, each one has got some degrees of freedom. I can describe all the particles in this room by counting all the degrees of freedom. It is amazing to realize that I could actually describe it equivalently by a theory that sits on, if you like, on the walls of the room, that doesn't come inside at all. And people have been able to do these things. What that has led some well-known physicists to conjecture is that, in fact, space and time are right now outdated, becoming rapidly outdated concepts. We might be getting ready for the next revolution in understanding of what it is that you have managed to call space and time and got along with for very long. It is not that they will become useless. They will still serve us very well. Newtonian physics is still excellent. You can send a probe to the moon using just Newtonian physics. But it is true that if you want to not go astray in your car, then your GPS actually better take the GR correction into account. So it depends on what you need to do. Similarly, space and time are perfectly good concepts. Special relativity works perfectly well. General relativity works perfectly well in the fields that we have tested it so far, as we heard with the discovery of gravitational waves. But one day we might find an environment where general relativity needs further correction because it is still a classical theory, it is not a quantum theory. And the nature of time, as was highlighted in the first talks today, in such a context will bear re-examination. We just don't have the mathematical tools to do that yet. And until we can do that, as I said, we are human beings, we question, we wonder, we doubt ourselves, that is perfectly natural and correct, but we should not be too disappointed that we cannot give clear answers to questions that are badly posed. And those questions are badly posed until we have the tools. So let me finish by quoting, since we're supposed to quote philosophers. This is a famous Greek philosopher that you have all heard of, and he said something that is rather telling. By convention there is color, by convention sweetness, by convention bitterness, but in reality there are atoms and space. Very far-sighted, since he never did a single experiment, but he saw it all. Reality, there's atoms and space, and David Gross, whose talk I've taken this from, who was the discoverer of quantum chromodynamics, or rather asymptotic freedom in non-abelian gauge theories. So his take on this is, by convention there is space, by convention time, as I've just outlined, but in reality there is, well, you'll have to wait till the next meeting in this series, perhaps, for that to be answered maybe a century from now. Thank you.
In case no one else is going to do this, may I say on behalf of all the participants, thank you very much, all of the speakers. What a fantastic meeting this has been. I've been tremendously stimulated by everything I've heard, and hopefully there will be more such meetings. Thank you very, very much.
Thank you.
Thank you all.